Another concept we talk about in this chapter is called radiation pressure. So when light hits a surface, that energy is partially transferred to the surface, completely transferred to the surface. It reflects, it could potentially reflect off the surface, but in any regard, because it hits the surface, it interacts with the surface and exerts a pressure. Now, pressure, if you recall from Physics 1, is the ratio of force applied divided by the area the force is applied on. So, for example, a chair. I'll pretend I can draw. So our chair has 4 legs, of course, I hope. I guess they don't have to, but if you sit on a chair or even just put something on the chair, we have the force of gravity of the chair itself and whatever may be on the chair downwards, meaning the feet of the chair are pushing on the ground. So if this is our ground, that mg, that total weight, is distributed over all 4 feet. So all 4 feet pushing on the ground is where the pressure would be experienced or felt by the ground. That would be very different than putting the same weight on a post that was thin, like the leg of a chair. All the weight over this one area would be a larger pressure, assuming this area is comparable to the area of one leg of the chair. So we're talking about pressure. This force per area is the force applied divided by the area that the force is actually applied over. Now, our author assumes all of the energy or radiation is completely absorbed. So as this electromagnetic radiation, some sort of light, it could be microwaves, X-rays, visible light. If it's completely absorbed, then this radiation pressure, this is how they write it in the book. It's a lowercase p with the subscript of RAD, is the intensity over the speed of light. Now, we could write this also as the S average over C, if you are not using I to not confuse it with current. Completely absorbed, that'd be, if you ever notice in the summer, if you have a black car or a black t-shirt on, the black gets really, really hot compared to a lighter color, and that's because that energy is completely absorbed, or mostly completely, very close to completely absorbed by the black colors. Now, something to be careful of in our test notes here. This radiation pressure line is written this way. So we take our knowledge of pressure from Physics 1 as pressure being a force per area, but then intensity, remember, is a power per area. So power per area. C is the speed of light, and that's where we get this I over C, or S average over C. In this relationship, these areas are not necessarily the same thing. They're not the same. When we talk about pressure, the area in the denominator here is the area the force is applied to. On the right side, when we're talking intensity being power per area, this area is the area the wave itself spreads over. These do not need to be the same thing. They could be. It depends upon the situation. So for example, if I go back to a light bulb example, I have a light bulb. I know its light is emitted in all directions uniformly. So the area in the intensity, power per area, this area would be the 4 pi r squared, telling me that any distance r in any direction from the light bulb is going to have the same intensity. So this would be the surface area of the sphere, because I can go out in any same direction and observe the same intensity. Now, minus the base, of course, but we're ignoring that part for all intents and purposes. Now, if we're talking about force, though, let's say I have a piece of paper over here. I didn't draw these lines long enough, but light would be traveling through the room. Some light would be hitting this paper. And so we would say that there is a radiation pressure so the P rad that we say is force per area. Well, if I'm talking about the radiation pressure on this paper, the force is applied to the area of the paper, not the surface area of the sphere. The paper does not completely encompass this light bulb. It only gets a portion of the light. And so in the radiation portion part, we would want the area of the paper itself in the force per area, whereas in the intensity portion, the power of that light bulb would be spreading out over a spherical surface or a spherical area. So be careful with those A's, those areas. They could be the same. The way they would be the same is if I had this piece of paper, but instead of a light bulb, if I had a laser pointer. So the light from the laser pointer coming and hitting the paper. The radiation pressure would be the force at that location divided by the area of just that little circle. I wouldn't want the area of all of the paper because not all of the paper is being hit by the light. The light is not shining on the entire paper. So I only need the area that the light is actually shining on because we're talking about the force or pressure from the light itself. The intensity of this light is the power of the laser pointer divided by this little circular area that the light spreads over. So in that case, the areas would be the same. So if I were to write out my equation, that radiation pressure is the force per area of that little tiny circle that the laser pointer makes, that would equal the power, I'm going to write out power so I don't confuse it with pressure, over the area of the little circle that all of that power is within. So area of the circle in this case would cancel. And that's because the light of a laser pointer spreads over just that little tiny circle, hence it's called a pointer. And that little circle doesn't enclose the entire paper. Whereas if we go back to the light bulb example, force per area of the paper would be our radiation pressure. This would have to be the power of the light bulb divided by 4 pi r squared. I'm just bringing this portion to power per area and then C. The 4 pi r squared would represent the area that the light or radiation from the light bulb spreads over. So if the wave spreads over a larger area than what we're talking about the force on, those areas are different. So I'm going to do a couple of example problems in separate videos so you can see how to use these equations.